pretty much our entire lives are online, and everything we do is protected by this invisible shield, a shield made of pure mathematics. Every password, every bank transaction, every single private message is kept safe by a very specific kind of math. But what if that math is about to break? Today, we're going to look at the future stability of our entire digital world. And yeah, that sounds like something out of a movie, right? But it's a very real question, one that keeps cryptographers and security experts up at night. Because the security we all just take for granted, well, it's not some unbreakable law of physics. It's built on something way more fragile. That's right, a bet. The whole foundation of modern digital security, the thing that protects literally everything, is basically a calculated gamble. It's a bet that certain mathematical problems are just so incredibly hard that no computer on Earth could possibly solve them in a reasonable amount of time. And to really get what this bet is all about, we've got to understand the rules of the game. So, let's dive in. To understand this great bet, we first need to get a handle on the rules. And it all boils down to how computer scientists sort problems based on one simple question. Is this thing easy or is it hard? Think of it like sorting your laundry. You've got your easy pile, your socks and t-shirts, and then you've got your hard pile, the stuff that needs special treatment. Well, in computer science, these piles have official names, and they have very, very specific rules. Okay, so here are the two big piles. On the left, we've got the easy problems. Officially, we call them P problems. Think about something like sorting a list of names. A computer can just blaze through that, no sweat. But on the right, we have the hard problems, known as NP problems. Now, a classic example here is finding the prime factors of a gigantic number. It is unbelievably difficult for a computer to solve it, but, and this is the key, if someone just gives you the answer, it's super easy to check if they're right. And that one simple difference, hard to solve, easy to check, is the bedrock of our entire digital security. And this, right here, this is the bet in a nutshell. The RSA algorithm, which is an absolute cornerstone of online security, is basically gambling. It's gambling that the problem of factoring big numbers belongs squarely in that hard NP pile, and that nobody will ever figure out a fast, clever way to drag it over into the easy P pile. And for decades, that bet has paid off beautifully. This is where the story gets really interesting. See, all these rules, all these bets we've made, they were all based on what we thought computers could do, what we call classical computers. But there's a new kind of computing on the horizon, one that, well, it doesn't play by the same rules at all. And that new player? It's the quantum computer. And it brings with it a totally revolutionary new algorithm that puts our entire digital security system right in its crosshairs. So meet Shor's algorithm. It is a brilliant, beautiful piece of mathematics designed to run specifically on a quantum computer. And its one incredible special skill is taking that exact problem we bet all of our security on, factoring huge numbers, and making it look easy. This chart just lays it all out, crystal clear. For a normal computer, a classical computer, factoring is hard. It's an NP problem. It's the whole basis for our digital lock. But for a quantum computer running Shor's algorithm, that very same problem becomes easy. It gets moved right over into the P pile. The lock that we thought was unbreakable, suddenly, there's a key. So let's be really clear about this. The moment a powerful enough quantum computer actually exists and can do this, our big bet is lost. It's over. RSA encryption and a massive chunk of the secure internet with it becomes completely worthless overnight. This isn't just some minor bug. It's what some people call a cryptographic apocalypse. But, okay, the story doesn't end there with total disaster because they can see this cliff up ahead. Some of the world's brightest minds are already in a frantic race to build a bridge to the other side. They're trying to invent a whole new kind of security, one based on a completely new kind of math. This whole effort is called post-quantum cryptography, or PQC for short. And the goal is actually pretty simple, even if the task is absolutely monumental. Find new mathematical problems to base our security on, problems that are hard for all computers, including the quantum ones. So the challenge now is to find a new bet, a new hard problem, one that stays firmly in that hard pile for everybody, even for a quantum computer. And right now, the most promising candidate is a field called lattice-based cryptography. The best way to picture it is like an incredibly complex, multidimensional grid, and your job is to find the shortest possible path between 2 points. As it turns out, that seems to be a problem that even quantum computers really struggle with. And that brings us right to this very moment. We are living in the middle of a high-stakes, almost invisible arms race. It's this massive global effort to completely re-engineer the mathematical foundations of our digital world before the old ones completely fall apart. And you have to understand the scale of this challenge is just immense. It's not enough to just invent the new math. After that, scientists and engineers all over the world have to agree on new global standards. And then, finally, every single piece of software and hardware, from your phone to bank servers to military systems, all of it has to be upgraded. It's truly one of the biggest technological migrations in human history. So we're left with this massive question. On one side, you've got researchers racing to build and perfect these new post-quantum locks. And on the other side, you have teams racing to build a quantum computer powerful enough to be the universal key. The security of our entire future really depends on who wins this race.